this slide, the first page of slide, lecture
Yes.
17.
Yes, sir.
Okay. So this lecture mainly I shall give through slides. So if you have any problem or any doubt, you should ask between the lectures. Okay. So welcome everyone. So today we will start the graph theory. This is the last portion of our syllabus. So we will have 6 lectures, and I have also told you that what are the days when these lectures will be done. So we start with the definition of graph. So graph can be multi-graph as well and also directed graph, but in this course mainly we focus on simple and undirected graph. But obviously, but in this lecture, in the today's lecture, we will see some results which hold for the multi-graph as well. Okay, but in general, that is in general in our this course we mainly focus on the simple graph. Maybe from the lecture 2 onwards, when we will say that graph coloring and then matching, everywhere we need just simple graph. Okay. So that is the reason I start with the definition of simple graph. So what is the simple and undirected graph? So a simple undirected graph is an ordered pair of two sets, and which is denoted as G, and the ordered pair is V comma E. So what is V? Now the elements of V are called vertices. Oh, there is a typo here. Okay, and the elements of E are called edges. Okay. Now what is the relation between V and E? So E is just subset of V cross V. More precisely, you can say that V is a E is a subset of V cross V minus this diagonal. That is, we remove the sets which is of the form U comma U, where U belongs to V. Okay. So that's mean any edge is of the form this way, right? Is a two element set, right? U comma V. But for simplicity, we generally write any edge by only this way, that is UV. So therefore, when we say edge, it means a two element set. Okay, and that two elements are from the set V. Okay, and these are called the end points or end vertices. Okay, so a simple graph is a ordered pair V comma E. Okay, where V is the vertices, is the edges, the set of edges, and the relation is the endpoints of the edges are the vertices only. Okay, so this is called a simple graph, but in general we can denote the graph which can be multi-graph, pseudo-graph. That's mean we will define that. So what is actually a graph? So a graph is an ordered pair of two sets denoted by V comma E, and where the elements of V are called vertices and the elements of E are called edges. Okay, and the elements of E are related with the elements of V in the sense that when we take an edge E, okay, then it has two endpoints which are vertices. That is the elements of V. Okay, that is a simple. That means it is just a collection of vertices and collection of edges. That's all. So generally we write this graph in terms of pictures. You know, so you will see some pictures as well. Now what is a loop? A loop means, so loop is an edge whose endpoints are same. Okay, so that's mean if you take a vertex say U, and if you join a say edge starting from U and again by come back to U again, right? Now it called a loop. Okay, and what is multiple edges or say parallel edges? Now suppose you have two vertices, say U and V, and then E1 and E2 are called multiple edges or parallel edges if they have the same endpoint. That's mean if you have two vertices u and v, and if you just draw two edges, edges means it not necessarily that it will be a straight line. You can choose a curve as well. Okay, so now if you join u and v by two lines, two say curves, then that two curves starting from u and ending at v are called parallel edges. Okay, so we can see first some examples. So this is one. So you can see here this is a loop. So for an example, if this is your u, and if you take this one, right, so it is starting and ending at the same point, right? This is called an loop. And if you look at this one, this is called a multiple edges or parallel edges. For an example, if this is your u and this is your v, then this is one edge and this is one edge. So these two edges, this and this, these two edges have the same end points. So therefore they are called parallel edges.
So why we made the parallel edges? What is the use of this parallel edges?
This is just a name. This is just a name. What is the use of parallel edges? Because for the graph theory, generally when we say that graph coloring and matching, there we need that this graph. This is called a simple graph. We will define that. But for some other purpose, we need this type of concept as well. For an example, we will see one application of this parallel edges as well. Okay, suppose you have two vertices, it might happen that there is no it is not only that single edge between these two vertices, it might happen that there are two or more edges between those two vertices. So there are huge applications of that as well. Okay, for that
Sir, there
we
E would be a multi-set in that case.
multi
The set of edges would be a multi-set in that case. Because
right,
we'll have
right. But we generally do not write in the set notation. Just write for that. See, only for the simple graph we told that E is a subset of V cross V. Okay, for the simple graph only. But when we say graph, we did not mention that E is a subset of V cross V, because we generally do not write when it is a multi-graph. We generally do not write in terms of UV.
okay, sir.
When there is exactly one edge between UV, then we write every edge as UV. But if there are multiple edges, then we do not write in that way. So we generally write in the arbitrary way, say E1 and E2 in that case, say in this way. Because it might happen that E1 is also UV, E2 is also UV, but they are different. Okay. So for the multiple edges or multi-graph, we generally do not write the edges as UV, as set notation. So set notation only applied for the simple graph. Okay.
Yes, sir. Thank you.
Good. So you should ask, because I might miss something. So if you ask, then it should be fine. It will be fine for me as well. Okay. So this is the notion of parallel edges. Now there is another notion called directed graph. So I am just defining this one. In our course, we do not use directed graph at all. Okay. So what is directed graph? So directed graph is again a graph. Okay, G, which is order pair V and E, that is my collection of vertices and collection of edges, and also E is a subset of this. But here we have a direction on the edges. Okay, we have a direction. So in the directed graph, we have a direction. For an example, we write here not a set, we write here in this way, that ordered pair U comma V. So here when you say directed graph, that ordered pair U comma V and V comma U, they are different. When you write U comma V, that means there is a direction from U to V. And if we write V comma U, then there is a direction from V to U. Okay. So we write in the first bracket. And for the simple graph, we write in this way, in the set notation. In here, UV and VU both are same. But for the directed graph, UV and VU, they are not same. Okay, because they have the opposite direction. But in our course, it is just for a definition purpose. In this course, we will not use the directed graph. but we will use multigraph, that is multiple edges, but we will not use the directed graph. Okay, so this is called directed graph. Now what is undirected graph? Undirected graph means it is just a graph where E has no direction. That's mean UV and VU both are same. Okay, so we mainly focus on the undirected graph. Okay, now what is a simple graph? Now simple graph is an undirected graph where loops and multiple edges are not allowed. So we have defined loops, we have defined multiple edges, right? Now if you take a graph, it might happen that that graph has some multiple edges or loops, but simple graph means loops and multiple edges are not allowed. Okay, this is called a simple graph. We have already defined that what is a simple graph. Now what is a multigraph? Now multigraph is a undirected graph where multiple edges are allowed but loops are not allowed. So these are the just terminology. You can say it is just a name. You have to remember those names. So when we say simple graph, there is no loop, no multiple edges. When we say that multigraph, so that's mean only multiple edges are allowed but loops are not allowed. And when we say pseudograph, that's mean you can add anything. You can add loops, you can add multiple edges. So here multiple edges and loops both are allowed. Okay. So in other way, you can say that a simple graph is also a multigraph. A multigraph is also a pseudograph. But a pseudograph may not be a multigraph, and a multigraph may not be a simple graph. Okay. So these are the subset. That is simple graph, this class of simple graph, subset of class of multigraph, that is subset of class of pseudograph. So is there any doubt of up to this? No, right? Okay, fine. Now this is the picture. So that's when see here in this graph, this is called a simple graph. Why? Because here you can see that there is no loop, there is no multiple edges, and also it is not directed. So this is called a simple graph. Now this is a multi-graph. Why it is a multi-graph? Because you can see there are multiple edges, this and this, right? But there is no loop, so therefore this is a multi-graph. And this is a pseudograph because here we have multiple edges as well as we have some loops. So therefore this is an example of pseudograph. And this is an example of directed graph. You can see that here we have edge between 1 and 2 vertex and we have a direction. Similarly, 2 to 4 we have a direction. So in this case, if these are the vertices, then we will say that it is ordered pair 2, 4. This edge is 2, 4. It is not 4, 2. Okay, this is 2, 4. For an example, these two edges are different. This edge is ordered pair 5, 4, and this edge is ordered pair 4, 5, because there is a direction from 4 to 5. Okay, but anyway, in this course we will not read this one, the directed graph. We'll totally omit this part in this course. Now in the directed graph, right? So we have defined directed graph in this way actually. This way, this one. We have seen that this is subset of U, V ordered pair, right? So therefore, in that sense, this is not actually directed graph. This is actually directed multigraph. So this is the definition. So a directed multigraph, okay. So is a collection of vertices and a collection of edges where each edge E has a direction, and here loops and multiple edges both are allowed. So this is just a there is no concept of directed pseudograph. So this is just a name. Okay, so this is called a directed multigraph where loops and multiple edges both are allowed and it has a direction as well. For an example, this is a directed multigraph. But in this course, we will omit everything in terms of directed. Here we read only the undirected graph. Okay, so that's why I have written here. So from now onward, we only focus on mainly simple and undirected graph. But here for some theorems is true for the multigraph as well. Okay, now there are lots of terminology, so you have to read, you have to sit and read, and you have to remember all of this terminology, because there are lots of things. If you attend only a lecture, it is not actually impossible to remember all of this term if you don't know this before. Okay, now first term is adjacent. Now two vertices U and V are called adjacent if there is an edge between U and V. Okay, if there is an edge between U and V, then we say that U and V, these vertices are adjacent. And if there is no edge between U and V, we will say that they are not adjacent. Okay. Now similarly, we have the terminology adjacent for the edges as well. Now so two edges are called adjacent if they have a common vertex. Okay. For an example, if you look at this, so this vertex, okay, right, this vertex and this vertex are adjacent, but this vertex and this vertex, they are not adjacent because there is no edge. Okay, and for the edge, this edge and this edge, they are adjacent. Similarly, this and this, they are adjacent. But if you look at this and the upper one, this horizontal one, this and this, they are not adjacent, right? Because they do not have any common vertex. This and this, they are not adjacent. So we use the term adjacent for the vertices and for the edges. Okay, but if you have one vertex and one edge, then we generally use the term incident. Okay, so between two vertex we use adjacent, between two edges we use adjacent, and one vertex, one edge we use incident. So what is an incident? So an edge E is said to be incident on U and on V if the edge E is just a UV. Okay, and similarly U and V are also said to be adjacent on E. Okay, so if E is an edge UV, then we say that E is adjacent to U, E is adjacent to V. Also we say that U is adjacent on E and V is adjacent on U, on E. Okay, oh sorry, not adjacent, incident. Okay, so I also sometimes confuse these two terms, adjacent and incident, but you remember that one. When you say between two vertices, you use adjacent. When you say between two edges, you use adjacent. When one vertex and when one edge, then we use incident. So therefore here, if U is an edge UV, then we say that E is incident with U and E is incident with V. Okay. Now this is another term, that degree of a vertex. Now degree of a vertex means it is the number of edges, okay, incident on the vertex V. So that's mean when we say the degree of a vertex, then you just count how many edges passes through the vertex V. And if you consider loop, then it contributes twice of the degree, because you can see that, you can see locally, if you have a loop, so it enters to the vertex twice. For an example here, what is the degree of this vertex? 3, right? 1, 2, 3. What is the degree of this vertex? 1. And what is the degree of this vertex? It is, can you say that? What is this?
5.
5. 1,
5.
2, 3, 4, 5. And what is this? This for this vertex? Again it is 5. 1, 2, 3, 4, 5. You just see locally. This is called a degree. Now there is another name. So if there is a vertex of degree 1, then it is called a pendant vertex. For an example, this one, it has degree 1, so it is called a pendant vertex. This is just a name, you can forget that one. And also, if there is a vertex with degree 0, then it is called an isolated vertex. For an example, suppose if with this simple graph, if we take another just a point here, then it will be called a isolated vertex. Okay, and in a simple graph, we say that a vertex has full degree, then if degree of V equal to number of vertices minus 1. Now it is also clear, right? Here it is right. Now here you can see that here we have 4 vertices, right? Now if you look at this vertex has degree 4 minus 1, that is 3. So therefore it is a full degree vertex, because this is the maximal one, right, for a simple graph. These are just terminology. So I cannot say that do you understand or not. This is just a terminology. If it is not clear, that is not, if yeah, if you want to remember this, you have to sit and you have to read. That's all. This is the only way to remember all of this term. Okay, now we are ready to state one lemma. This is very interesting and very useful lemma. It is called a handshaking lemma. So let G be a vertex, G be a graph, which is a collection of vertices and edges. Okay, and this cardinality of E denote the number of edges. Now then, summation of degree V equal to 2 times cardinality of E. Okay, so this is the lemma. It is called the handshaking lemma. Now this proof is very simple. What we will do, we will just count all the pair V comma E where V is a vertex of E. Okay, we just count all of these pairs, and we count in 2 different ways. What we will do, we first count V, how many V are there. Okay, so obviously number of vertices, and for each vertex V, how many E are there, it is called a degree of V, right? So therefore if we count V first and then E, then the total number of this pair will be this one, this sum, the summation of V belongs to capital V, degree of V. Is that clear? If we count V first and then E, then it will be this sum. Is that clear? Yes, if you have any doubt, you can ask. Is that fine to everyone?
Sir, can you explain once more?
Yeah. Okay. Suppose you first choose one particular vertex, one arbitrary vertex V. Okay. Now, what is the number of edges, or you can say what is the what are the numbers of this that pair V comma E, where V is an edge of E? How many pairs are there for a particular V? That is degree of V.
Yes, sir.
Right. Now if we run V to for each vertex V, then that will be this sum, and that will be a different pair, right?
Yes, sir. Got it.
Okay, so that's mean if we want to count at all the pairs V comma E, all the obviously different pairs where V is a vertex of E, then this will be this sum, that is summation of degree of V. Okay, so this is one way. Now if we count E first and then V, then you can see that if we first count E, choose a particular E, and for each E we can choose only 2 V, because any edge has 2 vertices only, 2 in vertices, right? So therefore for each edge we have only 2 vertex. So therefore if we count E, that is that cardinality, that number will be cardinality of E, right? And then for each edge we have only 2 vertex, so therefore these are the pairs is 2 times cardinality of E. Is that fine? So therefore we have, if we count V first, we get this one. If we count E first and then V, then we get this one. So therefore this equal to this. It is just a two-way counting, or you can say the double counting. This is a technique of double counting.
If we are in this group, we are counting the pairs like right V comma E.
Right. We are just
And then
counting
we
the
have
pairs, right? V comma E, all possible pairs, V comma E.
in two different ways.
Sorry.
In two different ways, we are counting the V comma E pairs in two different ways. Like first we consider the vertices. First we count the vertices.
Right. Then edge. This is one way, and another way is we count first E and then V. Okay. So for each V we have degree V number of edges, and for each E we have only two vertices. And this way we count all the pairs V comma E, and we get this equal to this. Is that fine to everyone? Yeah, that is very simple actually. You just now you can read. Now we have a corollary for that handshaking lemma. It says that let G be a graph, then G has even number of vertices of odd degree. Okay, for any graph G, you must have even number of vertices of odd degree. Why this is? Because we have already seen that this sum equal to 2E, or you can say that 2E equal to this sum. Now we separate this V, that is set of vertices, into two parts. One part is the even degree vertices, another part is odd degree vertices. Okay, so let V1 is the even degree vertices and V2 is be the set of odd degree vertices. So therefore 2E equal to this plus this, right? Now if we take this left hand side, then we will have this sum equal to this one. Now you can see that left side is even. Why? Because 2E, this is even, and here for each V belongs to V1, degree of V is even, so therefore this sum is also even. So left side is even, so therefore right side should be even, right? Now right side is even, but note that degree of V, for each V belongs to V2, degree of V is odd, and if you add odd numbers odd times, then you will again get odd numbers, but it is even, so therefore that number of V2 must be even, because if number of V2 is odd, then this sum will be odd. So therefore number of V2 is even. So we are done. So we have even number of vertices of odd degree. Is that fine with everyone? Yes.
Yes, sir.
Okay, good. Okay, now there are more terminology. So here generally people confuse with path, walk and trail. Okay, so you have to differ. So what are the path, what are the walk and what are the trail? So you have to differ that. So first of all, what is a path? Okay, so a path generally we denote by Pn is a graph which consists only n vertices, say V1, V2, V3 up to Vn, and since we are saying that exactly n vertices, that means they are different. Okay, so V1, V2 up to Vn, they are different vertices, and we have exactly n minus 1 edges, and these edges are V1, V2, V2, V3, V3, V4 and up to Vn minus 1 Vn. So this is called a path, and we generally call that Pn is a path between V1 and Vn. Okay, or you can say that V1 and Vn are connected by the path Pn. Okay, so this is the definition of path. Okay, so you have to remember that here V1, V2, Vn all are different. Now what is the definition of cycle? Now similar to path, a cycle Cn, or generally we write n cycle, is a graph consisting exactly n vertices and exactly n edges, and they are different. Okay, so for an example, here we have exactly n vertices are v1, v2, v3, vn, and exactly n, not arbitrary exactly n edges. These edges are v1, v2, v2, v3, v3, v4 up to vn minus 1 vn, and then vn v1. So these are the edges. Okay, so if for this, from this you can say that a cycle is also a path, but a path may not be a cycle, right? Because cycle is just a path with the endpoints are same. So any doubt on the definition of path and cycle?
Sir, a cycle would be consisting of two paths, right? I mean, in the definition, we have written exactly n vertices and exactly n minus 1 edges for paths. So we could say that a cycle is from v1 to vn and then vn to v1.
Right.
So there are two paths.
Right.
Okay.
There are two paths, and right, one path has length that is n minus 1 edges, and another path has only one single edge. Okay. Now there is another term called wheel. Wheel is not much useful here. Wheel means, suppose you have a cycle. Now if you join one extra vertex and connect, okay, I can show you the picture. So this is an wheel. So this is a cycle. Okay. Now if you join one extra vertex this, and if we add edges from this vertex to all of these vertices on the cycle, then we get a wheel. So this is 4 wheel, this is 5 wheel, this is 6 wheel, 7 wheel, 8 wheel, 9 wheel, in this way. Okay, this is not much useful here. Okay. Now this is important one. This is a walk. Now walk is very important. Okay. Now people always miss the term, that confuse with path and walk. Now what is walk? Walk is a sequence of vertices v1, v2, vn. Here it may be repeated. We are not saying that they are exactly n vertices. We are not saying that. This is a sequence where that vertices may be repeated. Okay. And we will say that this sequence of vertices is an walk if every pair of consecutive vertices are adjacent. That's mean we have edges v1, v2, v2, v3, v3, v4, in that way vn minus 1 vn. But here the difference is sum of vi and sum of vj may be same, and they might have common vertices, they might have common edges, everything. It is called walk. So a walk, I have written here, may have repeated vertices and repeated edges. Now if the in vertices are same, that is v1 and vn are same, then we say that it is a closed walk, and if they are different, we say that it is an open walk. So therefore from this we can say that a path is also a walk, that is an open walk, right? A cycle is a closed walk. But converse is not true. That's mean a walk may not be a path and a closed walk may not be a cycle. Is that fine? Path and walk? Yes?
Can you give an example of this walk, like repetition of vertices?
Okay. If you look at here, okay. Now see, if you start from this vertex, you can see my cursor, right? Can you see my cursor?
Yes, sir.
Yes, sir.
Okay. Now if you go to this, to this, to this, then this, then this. Now this will be a path. Path from this to this vertex. Now if we add this, and then this, then it will not be a path because these vertex are repeated. Okay, but this will be a walk. So therefore the walk will be this, 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 and this. This will be a walk. So walk can be anything. So for path you need distinct vertices and distinct edges, but for walk you may have everything. So for an example, from this vertex you can go first this, then this, again this. So you first go to this, then go back to this, again this. Then this will be again a walk. For an example, if you have a two vertex, say U and V, suppose you have UV, VU, UV, then this is also a walk between U and V. Okay, but when we say a path between say AV, UV, and if UV are same, only one edge, then you can see that only that one edge UV. Now UV, VU, UV, that is not a path because here edges and vertices all are repeated. But for a path, for a cycle, edges and vertices are not repeated. So am I understood? Yes.
Yes, sir.
Okay. Now this is walk. Now another term is called trail. Again, this is different from walk and path. Okay. Actually, it lies between walk and path. So a trail is a walk. It is a walk in which no edges is repeated. So here vertex can be repeated, but edges are not repeated. Okay. For an example, here in this example, we say that this, this. Now, is it a trial? Tell me.
Yes, sir.
Because here vertex, this vertex is repeated, but there is no the edges are not repeated, right? So this is a trial. But if we say that this, again this, so UV, VU, UV, is it a trial? No, because their edges were repeated, right? Now this is the difference between path, walk, and trial. Now there are two more terms that is very useful. One is Eulerian trial. So better to write, it is better to read as Eulerian trial. Okay, not Eulerian path. I generally avoid that term because this is not actually a path. If you say Eulerian path, but this is not a path. So better to practice to read Eulerian trial. Okay, I generally write Eulerian trial instead of Eulerian path because this is not a path. So what is an Eulerian trial? So let G be a graph, then an Eulerian trail in G is a trail such that it visits every edges of G and exactly once. Okay, for an example, in this example, if we take this one, 1, 2, 3, 4. Now this is one Eulerian trail, right? Because you have 1, 2, 3, 4 edges, and this trail visits all the edges 1, 2, 3, and then 4. So this is called a Eulerian trail. Okay. Okay. Now note that here I have already written this one. So Eulerian trail may not be a path because here edges are not repeated, but vertices can be repeated. As in the example I have shown you, right? One vertex was repeated. So therefore, this may not be a path. Now similarly, one can define Eulerian circuit. So what is an Eulerian circuit? Now Eulerian,
Sir,
yeah.
sir, what is the difference between Eulerian trail and normal trail that we are talking in the previous slide?
No, trail, right. Trail means it is just a trail. So I am not saying that here. It is, so every vertex will be here. For an example,
Okay, I understood. Yes, sir.
for an
We are
example, if
talking
you take
about
this
in a
vertex,
graph.
right.
Yes, sir. Yes.
For an example, here if we write only UV, now this is also a trail, right? But that is not a Eulerian trail because it does not contain all the edges.
Yes, sir.
Okay. Now similarly, you can define Eulerian circuit. So this means it is a trail, Eulerian trail, but the endpoints are same. Now again, by the similar note, we can say that Eulerian circuit may not be a cycle, because the name is Eulerian cycle, but it actually may not be a cycle. Why? Because vertices can be repeated. Okay. Now if in a graph Eulerian circuit exists, then the graph is called Eulerian. Okay. So if you will see a graph is Eulerian or not, Eulerian means there exists a Eulerian circuit in that graph. Okay. Now this is one Eulerian trail, Eulerian circuit. Now there are two terms. One is Hamiltonian path and Hamiltonian cycle. Now that is a path. Now Hamiltonian path means it is a path and it consists every vertex of G, and obviously exactly once because it is a path. Okay. So Hamiltonian path means it contains all the vertices of G, and Hamiltonian cycle means it is a cycle in G which contains every vertex of G, right? So when we say that Hamiltonian cycle, Hamiltonian path, we are not interested on edges, so we will miss many vertices. Sorry, we will miss many edges, but it should contain every vertex. Okay, we can see some one I have. For an example, this picture, you can see this picture. Now E means Eulerian, H means Hamiltonian. Okay. Now see, if you take only this graph with 4 vertex, 4 edges, this is just a cycle. Now you can see that this is also Eulerian graph and this is also Hamiltonian graph. Why? Because if you can start from here, you can go this to this, this and this. So that's when it is also a Hamiltonian cycle, right? Because it contains every edge, every vertex, and also it contains every edge. So therefore it is also Eulerian, right? So this graph is Hamiltonian as well as Eulerian. Now if you take this one, okay. Now see that this is a Eulerian path. Why? Why it is an Eulerian graph? Why? Because you can start from here, go this by the black cycle. So this to this, this to this and this, and then go with the green. So this. See, we have a walk, right, which contains every edges exactly once. So this is, therefore it is a Eulerian cycle, or you can say Eulerian circuit. So therefore this graph is Eulerian, but this is not Hamiltonian. You cannot find any cycle here which contains each vertex. You cannot find. Okay. So this is a Eulerian graph but not Hamiltonian. Now if we look at this one, now this is Hamiltonian but not Eulerian. Okay. You can check why it is not Eulerian. So, right. And similarly, this is not Eulerian, not Hamiltonian. Okay. Now you just try to find why it is Hamiltonian. Just you have to find the cycle. Okay. So I hope you understand what is the difference between Hamiltonian and what is the difference between Eulerian.
Sir,
Huh.
so in the third graph, there would be case that no edge is repeated.
Right.
Sir, if we move in the last, like the last corner,
Huh.
and then right to the right last corner, and then above, and
This
then
figure.
yes, sir.
Okay.
Then like from the last left corner to last right corner, and then the top right corner, top left corner, and then the inner triangle edge or the top of the triangle.
No, first of all, can you find one Hamiltonian cycle here? Can you tell me one Hamiltonian cycle here? Why it is Hamiltonian?
Uh,
You can go in this way. See, start from here, this to this.
yes,
So
sir.
we are removing this one. Okay. So then
Yes, sir.
this is a cycle with which involves every vertices. So therefore this graph is Hamiltonian. But this is not Eulerian because you cannot have any work which contains every edges once.
Okay.
For an example, you can go with or you can say this. Then this is missed, right? But we will have a theorem. So why this is not Eulerian? We will have a theorem. We will see that. Similarly, this is not Eulerian. We will see a theorem. So when you want to prove that a graph is Hamiltonian or a graph is Eulerian, it is easy to find. Just find one cycle, Hamiltonian cycle, or find one Hamiltonian Eulerian trail, right? So then you are done. But when you say that this graph is not Eulerian or not Hamiltonian, you cannot say you cannot find a cycle. You have to prove, right? So for that you have to use some theorem. So today we will see one theorem. By that theorem, you can see that this graph is not Eulerian. So I can tell you that what is statement of that theorem. That theorem says if you have an Eulerian graph, then degree of each vertex should be even. But here degree of this vertex is odd, so therefore you do not have any Eulerian cycle. Okay.
Yes, sir.
Okay. So now it is fine with you that what is the difference between Eulerian trail, Eulerian circuit, Hamiltonian path, and Hamiltonian cycle. So I suggest you, instead of reading Hamiltonian path, you better to read as Eulerian trail. Then you will not be confused. If you read as Eulerian path, and after some stage you will assume that it is a path, which is not. Okay. So some more terminology. So there are lots of terminology today's lecture. So what is a connected graph? Now a graph is called connected if there is a path between every pair of vertices. Okay. So if there is a path between every pair of vertices, then we say that that graph is connected graph. Otherwise, we say that the graph is disconnected graph. For an example, here every graph is connected, right? But if we assume this graph union with this graph, then this is not a connected graph because there is no path between this to this. Okay. Now what is the definition of acyclic graph? Now acyclic graph means it is a graph which has no cycle. So if a graph has no cycle, we call that graph is called acyclic graph. Now what is a tree? a connected acyclic graph is called a tree. Okay, so for an example, is this a tree or not? This simple graph is a tree?
No, sir.
No, because
sir.
it has a cycle, right? It has a
Cycle.
cycle, this one. Now, if we remove any one of the edges, this or this or this, then it will be a tree, right? Now, what is a subgraph? Actually, these are the clear from the definition. Subgraph means it is just a collection of v dash comma e dash, where v dash subset of v and e dash subset of e. That's all. Okay, it is called a subgraph. And what is a cut vertex? Cut vertex means a vertex v is called a cut vertex. If we remove that vertex and the corresponding edges, then you will have a disconnected graph. Or if your graph is already disconnected, then you will have one more component. Okay, for an example, if you take a connected graph and then we say that v is a cut vertex of that connected graph. If we remove the vertex v and the corresponding edges, that's mean remove only those edges which contains v, then you will get a disconnected graph. This is called a cut vertex. So similarly, you can define cut edge. So what is an cut edge? So if you remove one edge, then the graph will be disconnected, or you can say that one more connected components than G. Okay, not one, it can be more than, just say that more connected components than G. So it might happen that by removing one edge, you are getting, is it possible to find more connected components? No, I think exactly. Anyway, you can just say that more connected components than G. So connected components will be increased by one only in that case. Okay, so this cut vertex and cut edge, we will use these terms in the next lecture. Okay, now this is a famous problem. Okay, this is called a seven bridge of Königsberg. Now look at the figure, this one, and you can see that there are seven bridges: 1, 2, 3, 4, 5, 6, 7. Now this is the problem. Now this problem says, is it possible to take a walking tour of the town that crossed each of the seven bridges exactly once? Remember the term. So you have to take a tour. Okay, that's when you can roam around the city in such a way that you have to cross the bridge exactly once. Is it possible to have such a tour? And
No, sir.
in other way, there is another one, is it possible to start, that's mean that if we say that starting point and the ending point are same. Now is it possible to find to make a tour such that starting point and ending point both are same, and you have to cross each of the seven bridges exactly once? Okay, now one student give the answer no. So why you are saying no? Yes. So any argument of saying no? Okay. Now what we will do, we will actually just write these problems in terms of graph theory. What we will do, each portion, this portion we take as a vertex. So we have 1, 2, 3, 4. This 4 portion, right? This 4 portion will take as a vertex, and this portion, that's bridge, we will take as an edge. So we have this one. We have 4 portion, 1 green one, 2, 3 and 4, and we are writing this as a vertex.
Sir, we can say that you mentioned, right, or Eulerian cycle. To have an Eulerian cycle, all vertices must have an even degree.
Exactly,
So
exactly. Yeah, that is the same one. So you will prove that one only. Okay. So this figure is same as this figure, and this can be written as this graph theory problem. So this upper portion, green portion, we have taken as this vertex. This inside portion we have taken this vertex. The lower portion we have taken this vertex, and this portion we have taken this vertex. Now we can see that this portion is connected by two edges, two bridges. Therefore, this vertex and this vertex is connected by two edges. Similarly, this and this by two bridges. So this and this by two edges. Similarly, this portion by one bridge. So we have take one bridge. Okay. And similarly, this and this portion by one bridge. So one edge. This portion by one bridge. So one edge. So this one is same as this graph, and the problem is saying that do you have a Eulerian trail or Eulerian circuit in this graph? Do you have a Eulerian circuit in this graph? The second one, the second portion, is it possible to start at some place and take a walk, use each break exactly once and ends at the starting place? So it is the same as saying that does this graph has a Eulerian circuit? And for the first problem, the same as the saying that does this graph has a Eulerian trail? Okay, and both answers are no. And why this is no? By this theorem. Now this theorem says that if a graph G is an Eulerian graph, then all vertices of G are of even degree. Okay, so why? Now the proof is very simple. So what does it mean by a Eulerian graph? So that means since G is a Eulerian graph, so it contains an Eulerian tour W. Eulerian tour means you have a Eulerian circuit. That means you have a closed walk, right, which contains each edge exactly once, right, and vertices can be repeated, right. So better to write here it is a connected graph. So we will mention it is a connected graph. Okay. So assume that. Okay, it is fine if you know not assume it is connected. That is also fine. Okay. Anyway, so what we will do now? You have a Eulerian tour W, right? Now what we will do? We will trace the W. We will see that if we so what is W? W is a walk, a closed walk, right? Now if we start with some vertex, right, and if we can see here, better to see with one figure. Right. Now look at this one. This is Eulerian graph. So we can start with the second figure. Now start with this vertex. Okay. Now what is an Eulerian walk here? This one. This. Right. Again this. First the black cycle and then green cycle. Right. So this is a Eulerian circuit. Why? Because we have a closed walk which passes through each edge exactly once. Now look at this vertex. Now if we trace that W, this is called W. This cycle is called not cycle. This circuit is called W. Okay. Now see that start with this vertex. Okay. Now go this, and you are go to this and then removing this. So therefore when you pass through this one, now degree of this vertex is 2, right? You go and out. So there are two edges are involved for this walk. So the edges is 2, degree of this vertex is 2, and similarly go this and return this. Now we have again 2, now again 2, and come back to this one. So again 1. So we have 1 and again come back to 1. So therefore 1, 2, right? So therefore by this blue this cycle you have degree 2 for each vertex. Now again start with this green. Now again this go this. So again we increase 2. Now again we have 2. Again you have 2 degree. Again you have 2. So therefore degree of this vertex is 2 plus 2, 4. Degree of this vertex is 2. Degree of this vertex is again 2 plus 2, 4. Degree of this vertex is 2. Degree of this vertex is 2. Degree of this vertex is 2. Okay. So therefore when you have a Eulerian circuit, so therefore each time you are just adding 2 degree, right? You are adding 2 degree for that vertex. So if the vertex is repeated, if it is twice repeated, then it is 2 plus 2. If it is thrice repeated, then it is 2 plus 2 plus 2. If it is not repeated, then it is only 2. So therefore the degree of each vertex must be even. Is that clear to everyone? Yes.
Yes, sir.
So this is the proof actually. So this is a constructive proof, because your W, this Eulerian circuit W, involves each vertex, each edges, right? And when you trace this one, that is go out, go out, go out, and each go out you have 2 degree. So you have to just count how many ways it is going to just go and out. If one edge involves exactly once, then degree will be 2. If one edge involves twice, then degree 4. If one edge in one vertex involves 3 times, then degree will be 6 in this way. So degree is always even. And as a corollary, or you can say in the similar proof, you can prove that if G is a connected graph and G has an Euler path. Okay, Euler path means it has a Euler trail. Then all vertices of G except 2 has even degree. Now we are not interested on circuit, right? Okay, we are interested on only Eulerian trail.
Sir,
Now here,
could you go back to the examples that you'd shown of the Eulerian and Hamiltonian? Yeah,
this one.
Sir, in the third one, if I start from the top left, I go down, then right, then top, then move up again, then left, then the inner, and then the bottom one. Isn't that an Eulerian circuit?
You start from here.
I started from the top one.
No, you start here and finish here, right? You start from here and finish at here. It is not a starting point and ending point are not same. But yeah, but this is a good example. But this is an Eulerian trail. It is not an Eulerian cycle, but it is an Eulerian trail.
Okay, sir. Got it.
Okay. Now you can see that degree of this vertex is odd, degree of this vertex is odd, and degree of remaining vertex is even. So therefore we got the corollary, this corollary. So if a connected graph has an Eulerian trail or Eulerian path, then all the vertices except 2 have the even degree. And the why except 2? Because the starting vertex and end vertex have only 1 degree. For an example, this one. So it has an Eulerian trail as he suggested. So from this to this, so starting from here 1, 2, 3, 4, 5, 6. Okay, so starting from here, so we have this, so we have only 2, then go up 2, then this, then again it is here inverse 2, right? So you have only 2, and then again this and this. So for this you have 1, 1. So this vertex and this vertex has odd degree, and remaining other vertex has even degree. Okay, so it has a Eulerian, not circuit, but it has a Eulerian trail, and it has, you can see that all the vertices has degree 2 except 2. Okay, all the vertices except 2 vertices have degree 2. Sorry, degree even. Okay. Fine. Now by using this, you can say that, you can say no of this problem. Here you can see that degree of each vertex is odd. So therefore this is not possible. So Eulerian circuit is not possible, and Eulerian path, Eulerian trail is also not possible. Right. So therefore you have the answer no for these two. So this is also no, and this is also no, because it does not have any Eulerian trail and it does not have any Eulerian circuit. Okay, fine. Now this is the last one. So there is one term, that graph isomorphism. This is very simple. So suppose you have two graphs G1 and G2, okay, and we say that these two graphs are isomorphic if there is a bijective function f from V1 to V2 with the property that whenever u be an edge in first graph, then f of u, f of v is an edge in E2. Okay, then f is called an isomorphism between G1 and G2. Okay, so this is a trivial one. We will use that in the next lecture. And another one is adjacency matrix. Now again, we know what is adjacent, right? And here we are writing as adjacency matrix. So let G be a graph, and this is the vertex set. So V1, V2 up to n. So therefore, this graph G has n vertices. Now the adjacency matrix with respect to the vertex set V and with a fixed ordering V1, V2, Vn is a square matrix n cross n. Okay, and this square matrix Aij, where Aij is 1 if there is an edge between Vi and Vj, and it is 0 if there is no edge between Vi and Vj. Now obviously, since we are interested on simple graph, so therefore all the diagonal elements should be 0, right? Because there is no loop, so there is no graph, there is no edge between Vi and Vi, so therefore Aii is 0 always, so therefore the diagonal elements are 0. Okay, but this concept can be extended to the multigraph as well. So in that case, we can write Aij equal to 2 if there is 2 edges between Vi and Vj, and also we can extend this for the loop as well, or so we can allow the diagonal entry 1 for a loop. So you can say that, okay, we want to we want to take 2 for a loop. That is also fine. It is up to you. There is this is just the way you can define for adjacency matrix. So the adjacency matrix can be defined for the pseudograph as well. For multiple edges, you can count the number of edges, and for the loop, you can count either 1 or 2. Okay, but anyway, here in this course, we will use the adjacency matrix only for the simple graph. Now this is the last theorem. It says that, so let G be a graph with adjacency matrix A, okay, with respect to say ordering V1, V2 up to Vn. Now the theorem says the number of different walks of length r from Vi and Vj equals to the ijth entry of the adjacent of the matrix A to the power r. So walk of lengths r means, so how many edges are there of that walk. That is the call that of length r. For an example, if you take only A and if you take there is a edge between V1 and Vi and Vj, then we say that this is a walk of length 1. Okay. Now we prove this by mathematical induction. If we take n equal to 1, sorry, there is a typo. This will be small n. Okay. For the case small n equal to 1, you can see that Aij equal to 1 implies there is a walk of length 1 and Aij is 0 if there is no edge between these vertices, right? Therefore, the theorem is true for n equal to 1. Now we assume that the theorem is true for n equal to r, and we want to prove that that is true for n equal to r plus 1. So first of all, we take a to the power r equal to Bij. Okay, Bij means it is the entries of a to the power r. So by the induction hypothesis, Bij means the number of walks of length r between Vi and Vj, right, by the hypothesis. Now what is a power r plus 1? Now if you take n equal to r plus 1, then a power r plus 1 will be ar into a, and by multiplying you get that ijth entry is this one. Now what is bi1? Bi1 means it is the number of path or number of walk, not path, sorry, number of walk between Vi to V1. Okay, and A1j means the edges, that it is either 1 or 0. Okay, corresponding that V1 and Vj has edges or not. Okay, so this is the number of walks from of length r from Vi and Vk. So by the induction hypothesis, right, and this. So therefore, by the product rule, these are the all possible way. This is are the walk of this one, and these are the all possible ways of finding walk from Ai and Vi and Vj. So therefore, the statement is true for n equal to r plus 1. So this proves the result. And here we have an example. So for an example, we asked that what is the number of walks of length 4 from A to D, from A to D. So we first write the adjacency matrix. Now this is the matrix. See, so this is your A, B, C, D. So why diagonal entries are 0? Because there is no edges between A and A. This is 1 because there is an edge between A and B. This is also 1 because there is an edge between A and C. This is 0 because there is no edge between A and D, right? So in this way we write this matrix. Now by the theorem we have to find A power 4. Now A power 4 means this one. Now what is the number of walks of length 4 between A and D? So we have to take that 1/4 entry. Okay, so this one. So since this is 8, so therefore number of walks of length 4 from A to D is 8. So we are done. Now this 8th path from A to D of length 4. Okay. So these are all. So do you have any question? Okay, any question?